Okay, so this is a little bit late, but this is the quiz 4 solutions. Start with a couple of delta function questions. And one of them is kind of tricky. So here we have some function and evaluated, an integral evaluated over the entire real line, but the delta function is x minus 1. So nothing sneaky about that. That's just equal to the value of the function at x equals 1, where the argument of the delta function vanishes. So that's cosine of pi times 1, which is cosine of pi, which is minus 1. Okay, next one, a little bit tricky. So this is delta function of some function itself, namely g of x, in this case is x squared plus 4. And you can either use the direct expansion, or you can, you could try to argue from kind of first principles with a change of variables, which would be kind of tough because of the squared. But in general, if we have a function stuffed inside of a delta function, that becomes a sum over. So again, we care about all the places where the argument is 0. So we'll call them zeros of g of x. So we got to evaluate this at all of the places where g of x itself goes to 0. It is a delta function. And that's delta x minus xk. But if you were to do this from first principles, or you did the homework, you would have realized that when we do the change of variables, what we end up with is an inverse factor of the function itself evaluated at the derivative of the 0. So for us, we got two zeros, one at plus 2 and minus 2. This would be delta x minus 2. And what's the derivative of x squared minus 4 evaluated at 2? That's 2x times 2, so 4. Or 2x is 2 times 2. And then we have delta function x plus 2 also over 4. So I think the most common issue would be people missing this factor, which gives you the 4s. Okay. So this is sum of two delta functions, and we can take the 1/4 out front. However, only one of these vanishes inside the interval over which we're integrating. Oops, so that's a 2 minus 2. So we have a contribution from the x minus 2 argument delta function because our interval is minus 1 to 3. We do not have a contribution from this delta function because it never blows up, quote unquote, in between the interval of interest. It blows up at -2. Our interval starts at -1. So this just becomes 1/4. Just writing it all out, x minus 2 dx. So that's okay. And the 1/4 comes from the derivative evaluated at the 0. And then finally evaluating that, that's 1/4 times 2 cubed, or 8 divided by 4, or 2. Okay. Mostly just remember exotic properties, sort of exotic property of the delta function is that if we have a function inside of our delta function, we need to find that function zeros, but then there's also a term from the change of variables when you turn it into just a plain old ordinary delta function, 1 over the absolute value of the derivative evaluated at the zeros. So problem 2. Nice artistic problem. We'll just sketch the Fourier series of the following function. X squared evaluated on the region Okay, so the Fourier series expansion on the region -2 to 2, but the domain of the graph itself is -5 to 5. So really this is just asking you if you understand the basics of what a Fourier series expansion of a function itself is, to the point where you realize that it will repeat over the interval. Don't know why I drew the negative y-axis that big. It'll repeat over the interval -2 to 2. So if we plot this from -5 to 5, we'll get multiple periods. So 1, 2, 3, 4, 1, 2, 3, 4, 5, -1, 2, 3, 4, 5. Okay, and the statement of the question says, hey, we got a lot of terms. So we have a large number of terms. If there is a discontinuity in our graph, what we should do is we should maybe sketch the Gibbs phenomenon a little bit. But the region of expansion is -2 to 2. So that would get me up to 4 and 4. So far, so smooth. So we probably don't have any issues. But then so this is where the series expansion cuts off. Basically, you can think about this as a template. And I can take this, or stencil, and I can take the stencil and move it over to the next period. So from -5 to 5, we don't get all the way there. And likewise, the stencil repeats every every 4 units. Okay, do we have a Gibbs phenomenon there? Maybe if you look really close. More likely there would be a little bit of rounding because we're approximating an non-differentiable cusp with differentiable functions there. So if there is an issue, it would happen right at those tips. So that's really it. Just realize we're expanding over the region -2 to 2. That's the size of our stencil that we repeat. And if we were to draw that from -5 to 5, we would have 2.5 copies of that stencil. And then finally, compute a Fourier transform of a thing. And the recommendation is sketching it might help. So I trust me, so I'll sketch it. Won't make that mistake twice. We never go negative. So okay, the absolute value of t means that we're going to have a decaying exponential on the left-hand side and a decaying exponential as we go towards -infinity on the right-hand side to get something that looks like this. And we have a Fourier transform, so we're going to have an integral. So using consistent notation, little g to big G, and then x, that would go to k in the usual notation. 1 over √2 pi, integral over the entire real line, g, okay, so there's a t there and an x there. I never caught that. That would be omega then. Yeah, and I appreciate every single one of you guys seeing that using correct notation and then not telling me about the mistake so that you wounded me emotionally. Okay, so we should have an omega to match with the t to be consistent. Dt. Okay, this is piecewise continuous, so we have 2 different parts of this integral. We have from -infinity to 0 of e to the 2t, e to the -I omega t, dt. And then we have the part of the integral from 0 to infinity of e to the -2t, e to the I omega t. Oops, sorry, these are pluses. And even with an I in there, exponentials still have the multiplication rule as valid. So we get 2 plus I omega t dt, 1 over root 2 pi, 0 to infinity, and then the same thing, except we have a minus 2. So the plugging in, still okay. We have a complex valued coefficient, no problem. What we'll have to do is we'll have to argue the same way we argued in class about limits. So I have 1 over root 2 pi, and then I can just pull that out of everything. 1 over 2 plus I omega e2 plus I omega t evaluated at negative infinity and 0. Okay, so think sines and cosines. At 0, we can just plug this in and we get 1, no problem. But at the plus and minus infinities, we have an oscillating limit for the complex valued part. And you could either write it out, or you could just say, look, at worst case scenario, I have that oscillating Abel limit, which we already talked about. So the infinities are going to be 0. Depending on how carefully you make the argument, it's either 0 or 0. So you just end up with the evaluate at 0 terms left. And so that gives me 1 over 2 plus I omega, and then let's see, we get a minus, so, or plus minus. Oh, I skipped a step. So that's minus, but then we put another minus on there, so we could call that plus omega. And not a bad idea, we can rationalize these denominators. So for instance, we could multiply this by 2 plus I omega over 2 plus I omega. And likewise for this, we could multiply it top and bottom by 2 minus I omega to rationalize stuff, multiplying by 1 in a nice way to get a really nice answer, as it turns out. Should be 4 over 4 plus omega squared. So that is the Fourier transform of this kind of gunky looking piecewise continuous falling exponential. It turns out to be a really nice algebraic form.